Hello, my name is Abner, and today I will present the article Road Scheduling Strategies, Operational, Economic, and Environmental Performances for Waste, Electrical, and Electronic Equipment Collection and Transport in São Paulo State, Brazil. The authors are me, Abner, André Oliveira Nunes, João Eduardo Azevedo Ramos da Silva, and Virginia Aparecida da Silva Mores. I'm from UFSCar. Industrialization, marketing practices, population growth, and competitiveness have driven the expansion of industrial production, resulting in significant solid waste generation. This waste produced throughout the product life cycle, from raw material extraction to final disposal, not only leads to resource depletion, but also poses risks to human health and the environment. Among solid waste streams, waste electrical and electronic equipment stands out as the fastest growing worldwide, with an estimated annual increase of 3 and 5%. In 2022, 62 million tons of e-waste were generated globally. In Brazil, we had 2.4 million tons, but recycled only 3.6% of this waste. And the improper disposal of e-waste introduces environmental and health hazards due to toxic substances such as mercury and lead. At the same time, the recovery of e-waste presents significant economic opportunities as it contains valuable materials like gold and silver. To address these challenges, various countries have adopted specific policies for e-waste management, like European Union and Brazil. In Brazil, we have the National Policy on Solid Waste, which have the reverse logistics as a central mechanism for reintegration or proper disposal. Um, Reverse logistics systems for e-waste are complex, mainly due to some uncertainties related to quality, quantity, and infrastructure of returned products. Since transportation is both a major consumer of petroleum and a significant contributor to greenhouse gas emission, reducing transport and reverse logistics by optimizing roads, shortening travel distance, or increasing shipment loads is essential. So, in this context, the present studies analyzes data from a recycling company based in Sorocaba, Brazil, and this company collects waste, including computers, mobile phones, and printers, for individuals and organizations using a third-party logistics provider. With over 400 collect points, the company also collects cartridges and toners, primarily from major retail stores. The Southwest region, which includes São Paulo, Rio de Janeiro, Minas Gerais, and Espírito Santo, accounts for about 90% of Brazil's e-waste generation. And within this region, São Paulo alone is responsible for 92% of the total, and it is also the most populous Brazilian state, with over 44 million inhabitants in 2022. For this reason, this case study focuses especially on São Paulo state. So the aim of this paper is to propose a new e-waste collection scheme for this company in São Paulo using 6 scenarios. Well, the company under study recycles plastic from e-waste, including computers, printers, mobile phones, and cartridges. After collection and transport, the e-waste recycling process comprises disassembly, milling, extrusion, and pellet packaging. Core products such as ferrous metals, glass, aluminum, and etc. are sent to specialized companies for further treatment. To estimate the distance between each collection point and the company, the city where the third-party logistics provider collects the e-waste and the company's location in Sorocaba were considered. The distances were calculated using Google Maps. Um, Alternative transport network scenarios were analyzed using both an optimization model and a discrete event simulation. First, a road scheduling scheme similar to the milk run system was determined by analyzing the distance between the mesoregions regions of São Paulo state through the vehicle routing problem framework proposed by Arenales and others. This model aimed to find optimal routes to minimize total distance traveled by truck during waste collection. The mathematical formulation was implemented in GAMS Studio. For each scenario, the optimization model provided the optimal route, considering the amount of waste to be collected and the truck capacity with a predefined travel time limit. An exception was made for the metropolitan São Paulo mesoregion, which generates more UH than all other regions combined. For this area, a specific collection scheme with more frequent trips was adopted to accommodate its higher generation. Then, a descriptive simulation model was developed in Arena to assess the annual e-waste collection process based on the optimized routes and operational variables. We used stochastic distributions and we quantified the distance and some other data for uh, measuring the performance of this collection scheme. The model was developed under several key assumptions. The total volume of waste to be collected was based on data from November 2022. The state of São Paulo was divided into major regions with the collection center established in each one. Among the 15 official measurations, only 13 those with reported UAs were included in the analysis. A minimum frequency of one trip per month was set for each center except for metropolitan São Paulo region, which required more frequent trips. In cases where more than one monthly trip was necessary, the intervals between trips were modeled using an exponential distribution. Truck speed was represented by a triangular stochastic distribution, and all trucks unloaded at the recycling facility with unloading times following distributions between something like half and 1 hour, and each truck has a 3-ton capacity. 6 alternative scenarios were simulated reflecting incremental increases in e-waste generation, power measuration, and road scheduling with the objective of evaluating the system's ability to meet the target set by the sectorial agreement and the national policy solid waste. Scenario 1 considered the actual demand serving as the baseline for the measurations, while scenarios 2, 3, 4, 5, and 6 incorporated increases in demand and of 10, 20, 30, 40, and 50%, respectively. To assess environmental impacts, carbon emissions coefficients were used. One for electric vehicles, 0.078 kilograms of carbon dioxide per kilometer. And for internal combustion engine vehicles, we calculate the emissions in the Brazilian GAG program. We also compared in the 6 scenarios 2 possibilities using only internal combustion vehicles and using both internal combustion vehicles and electrical vehicles, but the electrical vehicles were used only in shorter distance, in this case, to collect e-waste in the metropolitan São Paulo Meso region. So in the results, we will see these comparisons. Economic evaluation considered 2 main components, labor cost and vehicle operation costs, and the labor was valued at $20.89 per hour and a cost of $0.13 per kilometer in electric vehicles and $0.17 per kilometer. So the total operational cost for each scenario was calculated by combining the total collection time and the total distance traveled as obtained from the simulation results. Well, about the results and discussion, in the current collection scenario, a single 3-ton truck is sufficient for most measurations, except for metropolitan São Paulo, which requires a distinct scheme to higher waste generation. The optimized vehicle routes obtained via VRP model minimize travel distance by grouping demands by measuration. Here we have 2 examples of roads in scenario 1, and in scenario 6 we need 1 truck in this and 2 trucks in the scenario 6. So the model representing the current scenario with trucks being dispatched to a specific measuration as soon as they are called has led to significant distance traveled and consequently high greenhouse gas emissions. In terms of cost, considering the current amount of waste generated, it is indeed approximately 26% lower than the proposed collection schedules when considering all internal combustion engine vehicles. So comparing the actual scheme with the proposed scheme in the milk run way. However, in all other scenarios, the current collection method performs poorly in the 3 aspects: environmental, operational, and economic. Compared to the first scenario, in scenario 6, with 50% more e-waste generation, experiences a 39% increase in the total distance traveled and a 36% increase in costs when considering only internal combustion engine vehicles. Overall, scenario 6 exhibits the highest total distance covered and associated costs, offset by a larger volume of collected e-waste. Scenarios 2, 3, and 4 demonstrate progressive increases in both distance traveled and cost. However, when comparing scenario 5 to scenario 4, a slight reduction in distance covered and approximately 1% in costs. So here we have a table with the results, and we can see that the actual scheme that is the scheme used by the company to collect the waste today. And here we have the proposed scheme generated by the optimal route and tested on the simulation. And as we can see in scenario 6, for example, we have here the total distance is less than in the actual scheme and the number of trips also. So we have here the results, and we can see that the proposed scheme, in fact, has a better result when compared to this one, the actual. Metropolitan region of São Paulo followed a schedule with shorter intervals between trips, 2.81 days in scenario 1, decreasing in the subsequent scenarios, and was responsible for most of the collected waste material. Consequently, a longer waiting time for collection in other cities would not significantly hinder the supply to the recycling company. In terms of cost, using an electric vehicle in the smarter distance can be costless. Scenarios under analysis were subject to temporal limitations. To elaborate, the operational window for the truck was confined to the hours of 8 a.m. and to 6 p.m. Should the time frame fall within this interval, the truck driver would opt for an overnight stay and undertake vehicle refueling as deemed necessary. This protocol diverted solely in the instance of São Paulo metropolitan area, wherein the journey, being comparatively shorter, adhered exclusively to the stipulated operational timetable. Here we have a table with the final results, and we can see the scenarios and the vehicles, such as the intercombustion, the use of internal combustion and electrical vehicles. The electrical vehicles were used only in the shorter distance, so to collect e-waste in the metropolitan São Paulo area, and the actual scan without the optimized routes. So as we can see here, in the scenario 6, for example, we have the cost in the with the use of only ICE and the use of ICE and EV have less cost than the in the actual scenario, and the same with the emissions, as we can see here. And this graph shows this. So as we can see, the actual scam is here higher than the other. So we have more costs, and if we see the scenarios, we have also more emissions, except for the scenario one, as I said before. But in the other scenarios, we have the the optimized roads performing better than the actual scam. So this paper evaluated the road scheduling strategy for e-waste collection and transport, considering operational, economic, and environmental aspects within a Brazilian case study. The results showed that implementing an optimized collection schedule can substantially reduce total distance traveled, numbers of trips, and greenhouse gas emissions. And although the routing strategy may initially increase operational costs, it proves more economical under higher demand scenarios, highlighting the value of fixed scheduling as e-waste volumes grows. This approach offers significant environmental and financial benefits, directly supporting cleaner production principles and demonstrating potential for sustainable improvements in reverse logistics systems. Thank you.